This is Dr. Shankaraiah from Department of Physics. In this presentation, I am going to discuss definition and terminology on Module 3, Lasers and Fiber Optics. Write the abbreviation of laser. The word laser is an acronym for light amplification by stimulated emission of radiation. So, laser, light, L for light, E for amplification, S for stimulated, E for emission, and R for radius, LASER, light amplification by stimulated emission of radiation. So that is the abbreviation of laser. Write the abbreviation of maser. Maser is an acronym for microwave amplification. Okay, M for microwave, A for amplification, S for stimulated, E for emission of radiation. Microwave amplification by stimulated emission of radiation. Laser is light amplification by stimulated emission of radiation, and maser is microwave amplification by stimulated emission of radiation. Define the term stimulated emission of radiation. Stimulated emission occurs when an atom or molecule in an energy level above the ground state interacts with a photon that has energy equal to that between an atom or molecule's current energy level and a lower energy level. Okay, so stimulated emission occurs only when an atom is in energy level E2, for example. E1 is the lower energy level and E2 is the upper energy level. So E2 is greater than E1. Atom is in higher energy level. Okay, so when we supply a photon, okay, when we supply, this is incident photon or input photon. Okay, incident photon. When we supply photon to the atom which is in the higher energy level E2, then this atom interacts with the photon and then this will decay to the, once it interacts with the photon, so next in the next stage, this atom will interact with the photon and it will decay to the ground state or lower energy level by emitting another photon. So there is incident photon. So this is photon 1, number 1, photon number 1, and this is number 1, that is the incident photon, and this emits another photon, and that is number 2. Okay, so stimulated emission occurs only when we supply a photon whose energy is equal to the energy difference. Okay, so then this atom interacts with the photon and decays to the lower energy level by emitting another photon whose energy is equal to the difference of these two energy levels. So H nu is equal to E2 minus E1. What is H nu? H nu is energy of the photon. H nu of energy of photons, two photons. Okay, so that is stimulated emission. Define the term spontaneous emission of radiation. If an atom is in an excited state, it may spontaneously decay into a lower energy level after some time, releasing energy in the form of a photon, which is emitted in a random direction. This process is called spontaneous emission. Previously, we have discussed about stimulated emission. For stimulated emission, we have to supply photon, okay, input photon, but for spontaneous emission, you don't need to supply any photons. Okay, so this is energy level E1, this is energy level E2. E2 is greater than E1. I mean, the energy of E2 is, this energy level is greater than the E1 energy level. Okay, so now atom is in E2. This atom, without supplying any photon, this atom decays to the, so next stage I want to, so this atom decays to the ground state. E1 I am saying the ground state and E2 is the excited state. Okay, so this atom in excited state going to decay spontaneously to ground state by emitting a photon whose energy is H nu, which is E2 minus E1. Okay, so this is spontaneous emission. In spontaneous emission, the atoms in the higher energy level or excited state decay to the ground state by emitting a photon, and this emission, decay from excited state to ground state is a spontaneous emission. Okay, we are not going to provide any energy or any photon to the atom in the higher energy. Define the term absorption of radiation. Absorption is the process in which optical energy is converted into internal energy of electron atoms or molecules. When a photon is observed, the energy may cause an electron and an atom to go from a lower energy level to higher energy level. Okay, so here we are not discussing about atom. We are discussing about we are not discussing about electron. We are discussing about atom. Okay, so yeah. Okay, so let us not go deep. So let us let us be at atomic level. So E2, E1 again. So absorption. So atom is in the ground state. For example, we know that E1 is less than E2 or E2 is greater than E1. So E2 is greater than E1. So atom which is in the ground state will go to the higher energy level excited state by absorbing a photon. So we are supplying input photon. So we are giving one photon. Then the atom which is in the ground state is going to excite to the higher energy level by absorbing this photon. So this atom is going to completely absorb the photon and get excited to the higher energy level E2. So that is called absorption. List the characteristics of a laser. Characteristics of a laser are directionality, coherence, monochromaticity and high intensity. So these are the 4 characteristics of laser light by which it differs from normal tube light. Define lifetime. An atom in an excited state does not instantaneously de-excite. The time that it spends on average in that excited level is called the lifetime of that state. Lifetimes can vary in duration depending on the atom and on the energy level. So lifetime is, for example, we are saying that atom which is in the ground state is excited to the higher energy level. So now atom is in the higher energy level E2. So this atom can undergo spontaneous emission. Now atom is in excited state, so it can decay spontaneously from E2 to E1. E2 to E1. Okay. So before decaying to the ground state E1, how much time does the atom spends in higher energy level E2? So that is called lifetime. The amount of time that is spent by an atom in a higher energy level is called lifetime. Okay. Define metastable state. Metastable state is an excited state of an atom or other system with a longer lifetime than the other excited state. Okay. Atoms in the metastable state remain excited for a considerable time in the order of 10 power minus 6 to 10 power minus 3 seconds. So what is the difference between metastable state and normal excited state? In normal excited state, the lifetime is about lifetime of atom in normal excited state. In normal excited state is 1 nanosecond, which is 10 power minus 9 seconds. Okay. But in a metastable state, the lifetime of atom is, let us say this is TLF. Okay. So the lifetime of the atom in metastable state. So this is metastable state. Metastable state lifetime is around 10 power minus 6 to 10 power minus 3 seconds. So it is more than the normal excited state. So if an atom is excited to a normal excited state, for 1 nanosecond it will stay in the normal excited state and then it can decay to the lower energy level by spontaneous emission. But if an atom is excited to the metastable state, it is going to stay for 1 microsecond to 1 millisecond. Okay, so it is going to stay for longer time. So the lifetime is more in metastable state compared to the normal excited state. How much more? 10 power 3 to 10 power 6 times more compared to the normal excited state. Define population inversion. When the population of higher excited state is more than the population of lower state, it is called population inversion. Population inversion is, okay, so now we have these 2 energy levels, so E1 and E2. So I am going to suppose there are some atoms in ground state. So the number of atoms is represented by N1. N1 is the number of atoms in ground state or energy level E1. And the number of atoms in the excited state E2 is N2. Okay. So N1 is greater than N2. If number of atoms in ground state are more compared to the number of atoms in the excited state, that is called equilibrium state. Equilibrium state or normal state. So normally more atoms will be in lower energy level compared to the higher energy level. Now there is another situation where number of atoms in, okay, so let me draw it here. Number of atoms in higher energy level are more. So let me draw here few. Okay, now E1, number of atoms in E1 is less compared to the number of atoms in E2. So N2 is greater than N1. When number of atoms in the excited state are more compared to the number of atoms in the ground state or lower energy level, that is called population inversion or inverted state. It is not normal state, it is inverted state or population inversion state. Population inversion state. Population inversion state or inverted state. Okay. So when N2 is greater than N1. What is the need to achieve population inversion? When population inversion is achieved, the majority of atoms are in the excited state. This causes amplification of the incident beam by stimulated emission. Thus, the laser beam is produced. Okay, so if you don't have the population inversion, you don't get stimulated emission, or when there is no stimulated emission, there will be no amplification of light. Okay, only when you have population inversion, that means, what do you mean by population inversion? More number of atoms are in the excited state E2 compared to the atoms in E1. When there are more number of atoms in the excited state, then these atoms can decay to the ground state through spontaneous emission or stimulated emission. Okay, whenever there is stimulated emission, the atoms will emit coherent photons, and these coherent photons are in phase. They will undergo constructive interference and intensity will increase. You will get amplification of light. So that is the reason why we need population inversion to get amplification of light through stimulated emission. Which process gives the laser its special properties as an optical source? In stimulated emission, the photon produced is of the same energy to the one which caused it. Hence, the light associated with the stimulated photon is in phase. Just now I discussed. Therefore, in contrast to spontaneous emission, coherent radiation is obtained. The coherent radiation phenomenon in laser provides amplification, thereby making a laser better optical source than LED. Okay. So because of these, because of the photons that are emitted in stimulated emission, the photons that are emitted in stimulated emission, so the atom emits one photon, then this atom emits another photon. So these photons are in the same phase. At a photon 1 and photon 2 and photon 3 and photon 4. All these photons are in phase. Because of this in phase, they will give constructive interference. Constructive interference and amplification will be more because intensity is directly proportional to amplitude square. Okay. So in phase, amplitude will increase and intensity will also increase. What is the law which can mention population of atoms in an energy state? Boltzmann distribution law specifies what fraction of atoms are found in an energy state for any given temperature. Okay, so that is exponential minus E2 minus E1 by kBT. Okay. So this will tell you the number of atoms in energy level E1, for example, and one is exponential minus E2 minus E1 by kBT, which will give you the fraction of ratio between the two atoms or number of atoms in excited state. So any energy level. So Boltzmann distribution is the law which will tell us the number of atoms or population in a given energy level at a given temperature. What is pumping in lasers? For maintaining a state of population inversion, atoms have to be raised continuously to excited state. It requires energy to be supplied to the system. So the process of supplying energy to the medium with a view to transfer it into the state of population inversion is known as pumping. Okay, so we want a laser beam. Laser beam is a amplified beam. And how did this amplification occur? The amplification occurred through stimulated emission. Okay, and stimulation can occur only when number of atoms in excited state are more compared to number of atoms in ground state. That means whenever we have population inversion, we can have stimulated emission. But to have this population inversion, there should be many atoms in the excited state. So how do we get many atoms in the excited state? We are going to supply energy to the atoms in the ground state so that they will absorb the energy and they will get excited to the higher energy level, so that we have the population inversion as a continuous system. Okay, so we will have the population inversion in a continuous manner, so that we have stimulated emission and amplification of light takes place, and we will get the continuous laser beam as the output from such a laser. So pumping is basically supplying energy to the atoms in the ground state so that they get excited to the higher energy level. What is optical pumping in lasers? Optical pumping is a process in which light is used to raise or pump electrons from a lower energy level in an atom or molecule to a higher energy level. So it is commonly used in laser construction to pump the active laser medium so as to achieve population inversion. So optical pumping, so we just now we have discussed what is a pumping. Pumping is nothing but supplying energy to the atoms in the ground state so that they absorb the energy and get excited to the higher energy level. Now, there are different kinds of pumping: optical pumping, electrical discharge. Okay, so optical pumping is nothing but we are supplying energy in the form of a light. Okay, so if you give light to the if you supply photon, which is nothing but light, so the atoms in the ground state can absorb and get excited to the atom. So for example, in ruby laser we use xenon flash lamp, and whenever this flash lamp give a flash, from the flash the energy is released and the atoms will absorb the energy from this flash, and then they will get excited to the higher energy. So basically light, we are using light. If we use light energy to atoms in the ground state, that is called optical pumping. What is electrical discharge pumping in laser? Yeah. In this method of pumping, electrical discharge acts as a pump source for our energy source. A high voltage electric discharge, flow of electrons, electric charge or electric current is passed through the laser medium or gas. The intense electric field accelerates the electrons to high speeds and they collide with neutral atoms in the gas. As a result, electrons in the lower energy state gains energy and they will get excited to the higher energy level. Okay, so basically electrical discharge is nothing but we are going to supply flow of electrons to the system of electric current into the gas, for example. Then these electrons which are present in this electric current will collide with the atoms, neutral atoms, and they will transfer the momentum to the atoms, and they will atoms can lose electrons or gain electrons, and they will become ions and they will move towards the electrodes, and that is how we will get excitation or pumping using this electric discharge. So by taking electrons from taking energy from electrons, the neutral atoms, first they can become ions, they can lose or gain electrons, and then they will get excited by taking momentum energy from the electrons. So that is how we achieve population inversion using this electric discharge as a pumping system. What type of lasers could cause skin cancer if not used properly? Excimer laser could cause skin cancer if not used properly. Yeah, so if you don't use the laser properly, it can give us the cancer. That laser is excimer laser. Okay, so this I have actually discussed already, so no need. So these are the characteristics of laser, 4 characteristics. Which one is a unique property of laser? Coherence is an important characteristic of laser beam because in laser beams the wave trains of same frequency are in phase. Due to high coherence, it results in an extremely high power. So coherence is an important property of lasers. Which type of laser is an example of optical pumping? The atoms of ruby are excited with the help of photons, emitted with the help of photons by an external optical source. So the atoms absorb energy from photons and raises to excited state. Therefore, ruby laser is an example of optical pumping, so which I have discussed already. Explain optical resonator in laser. An optical cavity, resonating cavity or optical resonator is an arrangement of mirrors that forms a standing wave cavity resonator for light waves. Okay, so optical cavities are major components of lasers surrounding the gain medium and providing feedback of the laser's light. Light confined in the cavity reflects multiple times, producing standing waves for certain resonant frequencies. So optical resonator is nothing but you have two mirrors, front mirror and back mirror. So there are two mirrors. In between these two mirrors, you have active medium. Okay, active medium is nothing but the active system plus active centers plus host medium. Okay, and this active medium will be connected to a pump so that you supply energy to this active medium, and then whenever there is stimulated emission, photons will be emitted, and the front one is partially reflecting and back one is 100% reflecting medium. These photons will these mirrors will provide feedback of the photons. So the photons that are touch these mirrors, they will get reflected back and they will supply into the system, and there will be more and more stimulated emission, hence amplification of light. What is the principle of fiber optical communication? In optical fibers, when light entering the fiber does not encounter any new surfaces, but repeatedly they hit the same surface. The reason for confining the light beam inside the fiber is the total internal reflection. So that principle for optical fiber communication is the total internal reflection. What are the different components of optical fibers? An optical fiber has core, cladding and jacket. So these are the three components: core, cladding and jacket as sheath. Define core of optical fiber. The core of a fiber is the region in which the light is guided. The core is a region of slightly increased refractive index. So core is the innermost region of the optical fiber and it has higher refractive index. Define cladding of the optical fiber. The cladding causes light to be confined to the core of the fiber by total internal reflection at the boundary between the two. It has a lower refractive index compared to the core. So core is innermost. This is the core, and next to the core there is cladding, and the advantage of cladding is that it confines the light into the core and it has lower refractive index compared to the cladding, compared to the core. Define Snell's law. Snell's law, also known as law of refraction, is an equation that relates the angle of incident light and the angle of transmitted light at an interface of two different mediums. Okay, so basically n1 sine theta I is equal to n2 sine theta r. Okay, so if you have incident and lay, then it can have refraction or transmission, and so this is incident angle is theta and having diffractive index n1, and theta r is the refracted angle of refraction, and this is n2. This medium has refractive index n2. Then we can write Snell's law of refraction: n1 sine theta I is equal to n2 sine theta r. So for incident and refracted light, you can use Snell's law. Define refractive index of a medium. Refractive index is also equal to the velocity of light of a given wavelength in empty space. N is equal to c by v, right? So divided by its velocity in the medium. So this is velocity of light and this is velocity in the medium. Velocity of light in wavelength in empty space divided by its velocity in the medium. Define acceptance angle. It is the maximum angle of a ray hitting the fiber core which allows the incident light to be guided by the core. So acceptance angle is the maximum angle by which we can launch the light into the fiber so that there can be total internal reflection. Define acceptance cone. If it is the cone in which light incident at an acceptance angle are less than the acceptance angle, and then the light can propagate to the fiber through total internal reflection. So acceptance cone, if you have acceptance angle theta I may be the maximum angle by which light can have total internal reflection, then so this is core and cladding, so then there will be a cone. If you rotate this angle about an axis, you will get a cone, and if you launch the light into the fiber in this cone, the light will propagate into the fiber through total internal reflection. Define numerical aperture. Numerical aperture is the light gathering capacity on optical fiber, and it is given by sine of acceptance angle. Define fractional refractive index change in an optical fiber. So fractional refractive index change is delta defined by n1 minus n2 by n1. So this is the fractional refractive index. How does the refractive index vary in graded index fiber? The refractive index of the core is maximum along the fiber axis and it gradually decreases as we go to core cladding interface. So it is so it is like this. So if this is the core, this is the core, the maximum refractive index is at the center of the core and decreases. The refractive index decreases as we go towards the core cladding interface, okay, to match with the cladding refractive index. Give reason for the distorted output. When rays travel through longer distances, there will be some difference in refracted angles. Hence, high angle rays arrive later than low angle rays. Therefore, the signal pulses are broadened, thereby resulted in distorted output. So, this is about losses, different losses. So, we can have distortion, and so this because of the distortion, there will be change in shape of the signal. Attenuation will be change in loss of amplitude. Okay, so this is because higher order and lower order modes in step index fiber. You will get this distortion. How scattering losses occurs inside the fiber? Scattering is a wavelength dependent loss. Since the glass is used in fabrication of fibers, the disordered structure of glass will make some vibrations in the refractive index inside the fiber, and this causes Rayleigh scattering. When more than one mode is propagating, how is it dispersed? When more than one mode is propagating through a fiber, then intermodal dispersion will occur. Since many modes are propagating, they will have different wavelengths and will take different time to propagate through the fiber. So this is because of the lower order and higher order modes, you will have this kind of dispersion. Explain about critical angle. Critical angle is defined as the angle of incident beyond which rays of light passing through a denser medium to the surface or a less dense medium are no longer refracted but totally reflected. Okay, so theta I, angle of incident, is greater than critical angle, only then you will have total internal reflection, and if not, if theta is less than theta C, you will have refraction and reflection, reflection and refraction. Theta is equal to theta C, also you have reflection, reflection and well as grazing of the light at the interface between core and clad. Define step index optical fiber. Step index fiber in which the core is of a uniform refractive index and there is a sharp decrease of the index of refraction at the cladding. So if you have core and cladding, so inside the core, in the core you have constant refractive index, and in the cladding also you have constant refractive index. So the refractive index of core will sharply decrease to match with the refractive index of cladding at the core cladding interface, and this is called step index optical fiber. Multimode optical fiber. Multimode fiber is a optical fiber designed to carry multiple light rays because of the high diameter of this fiber, and each is marginally different reflection angle inside the optical fiber core. Single mode optical fiber has small diameter, core diameter compared to the multimode optical fiber. Define refractive index profile in an optical fiber. A refractive index profile in an optical fiber is the radial distribution of refractive indices of materials within the optical fiber. Okay, so we are going to plot refractive index along y-axis and the distance along x-axis. So n versus r. So in the core you can have constant refractive index n1, and in the cladding also you can have constant refractive index n2. So then you will have sharp step-like profile, and this is called step index optical fiber. Define attenuation in optical fiber. So attenuation of optical fiber measures the amount of light lost between the input and output. Total attenuation is the sum of all losses. Optical losses of a fiber are usually expressed in decibels per kilometer. dB is nothing but decibels. So we measure the attenuation or losses of signal in terms of decibels per kilometer. What are the major components of optical fiber? The major components of optical fiber are transmitter, receiver, and optical fiber. Major components of optical fiber communication system. Okay, so optical fiber communication system has three major parts: transmitter, receiver, and optical fiber. Define gain medium of laser. A laser gain medium is a medium which can amplify the power light. Okay, power of light. So gain medium is a medium which can amplify the power of light, typically in the form of light wave. So this is a gain medium of laser. So these are some textbooks and references. To summarize, in this presentation I have discussed definition and terminology of module 3, which is lasers and fiber optics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.